The Rocky Mountains of the United States are covered with forests that are both vast and diverse, and encompass some of the most undeveloped and wild places left in the lower 48 states. Overall, they cover more than 100 million acres across 8 states of the interior West. The mountains that form what might be called the backbone of the continent stretch from west-central Canada in a southeast direction, diagonally across the western United States. Comprised of many different smaller mountain ranges, they are often referred to as the Northern, Central, and Southern Rockies because these regions are impacted by different weather patterns and offer different species assemblages and ecological processes that occur across this distance of more than 1,000 miles. One of the unique features of the Rocky Mountains is that they form an elevational barrier that the dominant and prevailing weather patterns must cross. Across the Rocky Mountains, east and north moving air masses must gain elevation to pass over the mountains, which results in the air cooling and causing moisture to condense at higher elevations and drop as rain or snow. The Central and Southern Rockies also affect weather patterns in a similar manner. They'll form a barrier to both east-moving air masses from the Pacific and northwest-moving air masses that originate in the humid Gulf of Mexico. The same condensation in the form of rain and snow occurs in these mountains, and one example are the notorious snowstorms that shut down the busy Denver airport, causing flight delays across the country. The Rocky Mountains are the continental divide and primary water collectors across an otherwise arid interior West, and form the headwaters for most of the major waterways of the West and Central United States. That includes the Columbia River system in the Northwest, east-flowing Missouri, Platte, and eventually Mississippi watersheds to the east, and the Rio Grande and Colorado rivers to the southeast and southwest. Any long-term changes in the prevailing weather patterns and their interactions with this mountainous spine of the continent, caused by either natural or human-modified climatic fluctuations, can result in significant changes to the moisture-limited ecosystems of the Rocky Mountains. In an otherwise arid West, water is one of the most important components that provides for different life forms and ecosystems, defined by the plant and wildlife species that occur across the landscape. Human populations and their livelihoods are equally dependent on the water and ecosystems created by water quantity and quality. It is important to recognize that the forests across the mountains play an important role of collecting this water, filtering it, and storing it. These same forests, however, are also vulnerable to changes in weather and climatic patterns that influence annual moisture. The snow and rain that the Rocky Mountains intercept from prevailing weather patterns has allowed for highly diverse forest ecosystems to develop across this landscape since the last ice age ended over 10,000 years ago. Depending on the mountain range and the location within that mountain range, differences in annual precipitation can result in wetter forest types, defined by cedar, hemlock, spruce, and true fir species, common to the northwest portions of the northern Rocky Mountains. Subalpine fir, spruce, and lodgepole pine on higher elevation sites, characterized by cold temperatures and winter snow accumulations, and warmer, drier forest types of ponderosa pine and Douglas fir that occupy the mid to lower elevations, all of which are commonly found across both the northern and central Rockies. And across the southern Rockies, the heat and drought-tolerant juniper, ponderosa, and pinyon pines. The diverse topography of the high mountain ranges and broad valleys characterized by the landscapes within the Rocky Mountains also interact with the climate and influence local weather patterns. Valleys act as solar collectors, and rising hot air allows for the formation of convection-based storm clouds that bring with them lightning. Each storm can produce thousands of lightning strikes, which can in turn ignite wildfires. For example, one storm in the year 2000 that crossed southwest Montana was recorded to have produced more than 80,000 lightning strikes in one day that ignited hundreds of wildfires. This contributed to more than 1 million acres of forest that burned across the state of Montana in that year alone. Wildfires have been a natural part of the history and development of forests across the Rocky Mountains for thousands of years. Their impact varies by the weather conditions when they burn and the fuel types in which they burn. Fires burning under mild conditions and lower fuel densities can act as thinning agents that thin out overly dense forests, and that can promote old trees to develop by thinning out overly dense groups of trees, which leaves good space for remaining trees to acquire adequate soil moisture and sunlight needed for them to grow bigger and live longer, such as the ponderosa pine and larch in this picture. Or wildfires can become forest-replacing fires where hundreds to thousands of acres of trees are killed across a landscape. Thus, wildfires can help create and conserve complex forest ecosystems, or they can also simplify and damage forest ecosystems. Much depends on the timing of the fire and the vegetation, fuel loading, and fuel conditions in which the fire burns. In the most severe burns, forests may be replaced in the long term with shrub fields and grasslands. Much depends on which tree species are present within the burned areas and how severe the fire effects were. In recent decades, more and more landscapes are experiencing very severe fire effects due to the combination of extreme summer droughts, lightning storms, and very high forest fuel conditions. An overall loss of forested area has been the result across many Rocky Mountain landscapes. Wildfires are, however, not the only tree-killing events across the Rocky Mountains. Over the past 2 decades, a very small and seemingly insignificant creature called a bark beetle has had an enormous impact on forests across the entire Rocky Mountains. Although native to these forests, bark beetles survive by feeding on and laying their eggs in the nutrient-rich inner bark of trees. Every pair of adult beetles lays between 30 and 100 eggs in their short 3 to 6 month lifespan. This means within 5 life cycles, over 5 years, 2 beetles can potentially grow into 5 million beetles. Since they have co-evolved with the trees they feed on, typically only stressed trees that lack the energy or water to defend themselves can be successfully attacked, which keeps beetle populations under control. There are more than 114 species of bark beetles across the Rocky Mountains, although only a few species are capable of killing live trees. Under the right conditions, where forests are overly dense with trees and summer drought and warmer than usual winters occur, these specific bark beetle populations can rapidly grow from inhabiting a few stressed trees to an epidemic that impacts hundreds to thousands of acres and billions of trees. Over the past 2 decades, all of these factors contributed to more than half of the 100 million acres of forested land across the Rocky Mountains suffering from bark beetle mortality. Although bark beetles can rarely kill all the trees in a forest, during an outbreak such that occurred in the Rocky Mountains this past decade, they killed between 30 and 90% of the trees across the landscapes they impacted, which was mostly forest dense with mature ponderosa pine, lodgepole pine, pinyon pine, and Douglas fir trees. Although dead trees are habitat for a variety of wildlife, including cavity nesting and bark-gleaning birds and woodpeckers, flying and pine squirrels, and owls and other small predators, dead standing trees do start to fall over anywhere between 3 and 20 years after they die. Too many dead trees in a fallen-over configuration also has its trade-offs. Complex, coarse, woody debris in forests has uses for certain wildlife, such as hiding in denning cover for snowshoe hares and lynx. However, too much of a good thing can also have severe negative side effects. Whereas patches of dead trees provides important habitat for specific wildlife, extensive landscapes with high fuel conditions create significant probability of severe wildfire effects. As previously mentioned, a warming climate in recent decades has predisposed forest areas with high fuel loading to burn with extreme wildfire behavior, which can be costly to try to contain and can have negative residual impacts. Dense forests with high fuel loading burn at high temperatures and for long durations. With the exception of certain species such as lodgepole pine that produce fire-resilient cones that can protect seeds from extreme temperatures, most forest types that experience severe fire effects across a large area recover very slowly and often not to trees. In addition, when entire watersheds burn with severe fire effects, hydrological processes can also be impacted that can include flood and reduced drainage water holding capacity. Landscape-level fires also burn into areas with human habitation and threaten people, homes, and infrastructure. Although wildfires can have positive impacts to wildlife, the more extensive a wildfire across a landscape, the higher probability that wildlife will get trapped and suffer dire consequences as well. Humans owe their success as a species to their ability to adapt and influence their environment. With increased knowledge of how our forests, landscape, and climate interact, also comes the recognition that the vast forest ecosystems of the Rocky Mountains that we depend on for water, recreation, fiber, and spiritual renewal are vulnerable to dramatic changes. The questions of how we are to interact with these forests and how and if we can help conserve them are complex. They include a thorough examination of tree species, the agents such as bark beetles and fire that impact different species, forest ecosystem functions, and landscape interactions with climate, including the role of greenhouse gases and how these forests can either add to them or capture and store these harmful byproducts of human existence. Forest management techniques that have been examined as both a preventative measure by thinning overly dense forests to alleviate extreme competition for soil moisture and thus boosting residual trees' defensive capabilities, and as a means to salvage some of the beetle-killed trees for wood products and as alternative feedstock for energy production. Preventative thinning of forests has shown that residual trees exhibit some greater resilience to bark beetle attack, though high beetle populations can mass attack and kill even healthy trees. The bark beetle outbreak of the past decade has been of such magnitude that even forests treated by preventative forest manipulations have in some situations been overwhelmed by the scale of the beetle population growth, leaving millions of acres of forest with excessive dead trees. Depending on the tree species, the wood of beetle-killed trees may remain usable for several years for traditional wood products such as lumber, or degrade within several months after beetle attack, where its uses would only be paper or energy production. Overall, there is much more impacted forest across the Rocky Mountains than is currently being utilized by the existing forest products infrastructure. Harvesting beetle-killed trees presents significant challenges as well. Beetle-killed trees are often brittle and fall into complex matrices of jumbled tree stems. Any person entering these forest conditions to try to harvest the trees using old techniques of logging with a chainsaw, or even recreational users such as hikers and hunters, are at risk of injury from falling tree stems. Modern tree harvesting across the Rocky Mountains, however, is no longer simple work with axes and saws, but is rather a high-tech, high-investment skill. Trees are harvested by specifically designed machines that can traverse difficult terrain, protect the operator within a reinforced steel cab, and can reach out and cut a tree and process it into desired lengths, all within minutes. Processed logs are then collected and transported out of the forest with other high-tech machinery operating on low-impact tire or track systems. Such machinery is expensive, and the average logging contractor that owns a harvester, log forwarder, bulldozer, and logging truck has several $1 million invested in their equipment. Training time to become proficient in using and maintaining this equipment ranges between 3 and 5 years. Modern loggers are highly skilled and trained contractors. Low-impact harvesting by modern equipment can be done in such a way that forests with overly dense trees or accumulations of dead trees can be treated to leave behind a functioning forest ecosystem that is also at lower risk to severe wildfire behavior and exotic noxious weed invasion. Since the forest species and conditions across the Rocky Mountains are highly diverse, forest management activities can be adapted to create different density forests, provide and protect important snags for cavity nesting birds, forest diversity for wildlife, recreational opportunities for humans, and clean water and snow collectors for the greater watershed. It is important to realize that this kind of adaptive management is site-specific, and how and what treatment occurs will depend on each forested site, the level of fuels accumulation, the different tree species that grow there, wildlife needs, water protection, and the objectives of the landowner. There also remain many research questions regarding how forest management practices are best integrated with natural forest processes and function. One of these is the role of woody debris in forest function. As previously mentioned, dead trees and fallen over woody debris does have some function for wildlife habitat, soil development, nutrient cycling, and forest vegetation and important microbial activity. Depending on the forest site, logs may persist for centuries because the local climate is too hot and dry for wood decay. On such sites, the risk from severe wildfire and negative impacts that too much woody debris can have on soils and vegetation may warrant the removal of excessive dead woody materials. Some states, like Montana, actually have laws that require that any woody debris generated by forest management activities be treated to reduce wildfire behavior during hot, dry conditions. Typically, excess woody materials generated by forest thinning or harvesting is pushed into piles using specialized equipment during or after the harvesting work on site. These piles may be multiple small piles or a few very large piles, depending on the type of harvesting that was prescribed and the equipment that was used to harvest and process trees. When environmental conditions are safe for burning and air conditions exist that will disperse smoke, these piles are ignited in order to reduce these excessive fuels to ashes. Small burn piles can actually be used as site preparation techniques for the recruitment of new tree species whose seeds require fire-impacted soil surfaces to germinate, thus emulating the processes that past low-intensity wildfires created. Larger piles are more cost-effective to create and burn, and are often used to lower the costs associated with forest improvement practices and fuels reduction. This brings up an equally important other part of forest management practices, the cost and benefit of such treatments. Wood is one of our most useful renewable resources. The traditional wood products industry uses logs harvested from many different forest ownerships that include family farms, state and tribal lands, and national forest to produce lumber for houses and other buildings, furniture, fences, posts and poles, playgrounds, paper products, wooden spoons, and hundreds of other products. And in Montana alone, more than 8,000 people are employed by the wood products industry. If the wood has been degraded to the point where it cannot be sawn into lumber, it traditionally has been chipped and processed for wood fiber that is used to make paper, panels, flooring, and other manufactured wood products, as well as wood-based extractives such as sugar, food flavorings, paint, and other chemical products that are also made out of coal and fossil fuels. Yes, it may be shocking to learn that many of the flavors used in our food products today start out as crude oil. They could have been made out of wood that was grown and harvested from a clean Rocky Mountain environment instead. Another very important use for beetle-killed and degraded wood that cannot be used for traditional wood products is energy. Although many people have experienced the warmth from a campfire, fireplace, or wood stove across the United States, there are far too few power plants that use wood chips, pellets, or gasified wood to produce heat and electricity. Although this is a common practice across Scandinavia and other European countries, cheap coal and natural gas has made it less common across the U.S. There are, however, emerging successful examples. The Montana-based Stoltz Land and Lumber Company has recently built a 2.5 megawatt power plant that was engineered to operate on wood waste from the sawmill and sustainable forest practices. Instead of burning woody residue piles in the forest, this material is chipped and burned in the power plant. This bioenergy plant provides more than 2,000 homes with their annual electricity needs. But to operate it, it requires approximately 67,000 tons, or 2,240 truckloads of beetle-killed trees and woody residues per year. This sounds like a lot, but in reality, this supply quantity represents the average number of trees harvested from only 750 acres. For example, consider that 25 million acres of forest from across Montana have more than 5 million acres with 30 to 90% of the trees killed by beetles, about 7 million acres that have been impacted by wildfires over the past 20 years, and another 8 million acres of multiple-use designated national forest with overly dense forest conditions at great risk from additional beetle attacks and severe wildfire effects. There are also other emerging new uses of wood that are still being developed for excessive beetle-killed trees and woody residue from forest management practices. We build structures out of wood because it is a relatively stable organic compound that resists decay and breakage. Therefore, wood is chipped to increase the surface area to mass ratio that improves its conversion into its basic building blocks of cellulose, starch, sugar, and lignin. New technologies allow wood to be digested by enzymes and turned into sugar, which is in turn fermented into alcohol that can be used as jet fuel or gasoline supplements. A side product of this process may be bioplastic that would replace current plastics made from fossil fuels. Another technology heats wood in an oxygen-free environment and is called pyrolysis. In this process, the sugars, starches, and lignins are gasified and condensed back into a liquid gasoline alternative, and the cellulose is converted into biochar. Biochar is basically a highly purified form of charcoal, where the wood structure has been turned into a crystallized and highly porous form of negatively charged carbon, that has many potential commercial uses, such as an organic filter to purify water, and as a soil additive that increases fertilizer efficiency and water holding capacity, that in turn increases irrigation and fertilizer effectiveness and crop productivity, while also reducing soil nutrient runoff into streams. Two additional long-term benefits are that atmospheric carbon dioxide, considered one of the main greenhouse gases responsible for potential changes to our climate, is captured by trees and turned into both biochar that can store carbon in the soil for up to 1,000 years and alternative liquid fuels to those currently produced from fossil fuels. Thus, the wood from forests that are too dense, beetle-killed fuel for wildfires, and waste products from sawmills can be converted into highly useful commercial products that we need while also helping reduce greenhouse gases. So why is this technology not in greater use today throughout the United States? There are three main concepts that must be addressed. First, wood is a low-density product compared to traditional fossil fuels such as coal or oil, which means relatively large quantities are needed to support the investment into a commercially viable infrastructure that produces biochar and bioenergy. This in turn requires extensive landscapes that can grow trees that do not compete with the world's food production needs. Second, the cost of converting wood into energy as a standalone industry is relatively expensive compared to using denser and more concentrated fossil fuels. And wood remains a valuable resource for our traditional wood products industry that turns tree stems into multiple high-value products that house, clothe, and feed us. Thus, wood-based bioenergy and carbon sequestration investments might be most effective when created in cooperation with existing or new wood processing facilities that allows optimization of every part of tree harvesting, transport, and processing. Examples of this concept have been pursued by many European countries, where sawmills are only part of a log processing facility that also includes an energy production plant and alternative wood conversion to biochemical products. Currently, many U.S. sawmill residues or wood chips are transported hundreds of miles to secondary markets. Third, to build new or modernize existing wood processing facilities and to justify such monetary investment requires forests that are healthy, resilient, growing, and available for the sustainable harvesting of wood every year for decades or even centuries. Forests across the Rocky Mountains are complex, and their ecological role, as well as the social expectations and understanding of them, varies tremendously across landscapes and communities. Climate change has resulted in insects and diseases showing us which trees are stressed or even genetically resistant to their attackers, and management practices should be used to accelerate the development of tree species and forest resilience to pests, wildfire, and drought. Forest management practices have benefited much from scientific studies that give forest managers the ability to understand how different forest harvesting practices applied to different tree species on the appropriate landscapes and sites can benefit trees by giving them the conditions to grow to their potential. Growing forests is not that different from growing other crops. Good management practices result in productive landscapes and sustainable ecosystems. Alternatively, poor management decisions can lead to failures and soil and site degradation. Forests are also very different from other forms of agriculture because trees take much longer to grow to their full potential size, and forests are not only comprised of many different species with different capabilities and functions, they are also the only landscape where management actions can provide products for human existence while also providing the habitat and environment for all the original native species that existed there prior to human development pressures. Historical natural processes need to be incorporated into landscape management practices across the Rocky Mountains, but only at a scale that reflect current forest conditions and climatic trends. Wilderness areas and other protected areas are also an important component to the landscape mosaic. However, the role of management activities on a landscape and timescale that provides actual positive impacts across landscapes is equally essential. No one solution works for every forested site, and determining where and when to use management interventions remains a societal issue that must rely on the experience and knowledge of natural resource managers, scientists, landowners, and an engaged public. A productive, integrated, and economically viable industry that can utilize the harvest from forest management and conservation will not only facilitate the massive scale of work needed across the Rocky Mountain landscapes,
It will generate revenues that can be used to conserve landscapes that produce less marketable products such as clean air, great views, the opportunity for solitude, and landscapes that support this nation's original wildlife and plant communities.